All right, let's get started. So this is the last unit of the course. It's going to be on transformers and large language models. So let's start with a little bit of background on what we've done so far. So when we studied deep neural networks, we focused on convolution. And convolution makes sense for some kinds of signals. Here we have just a depiction of convolution in one dimension where you have a sequence. And as we know, convolution, what it does is it takes a kernel and it slides that kernel across the sequence and uses the kernel weights as a weighted linear combination of these features to give this, and then a linear combination of these would give the next one, and so on. And that makes sense in some sequence processing tasks. Maybe these are samples of like a stock market sequence or something, and in that case, a kernel could be used to sort of reduce noise or look for jumps. You know, you can design kernels to do different things. And it's even more powerful if this is just one layer in a network that includes many layers of such convolution processing, and then you can get nice hierarchical representations, as we saw with deep convolutional neural networks. But not all signals work this way, where you have this sort of local structure that is space invariant or time invariant. So, for example, if you look at language, maybe we have a sentence, and the different words in the sentence have different roles in that particular sentence. So, Mary in this case is the subject, gave is the action. There's giving roses, there's giving roses to Susan, and so on. And there's these interrelationships between all these different words. But then if I give you a different sentence, you're going to find that the location of the word, like the location of the subject and the verb, they could have changed. So there's really nothing repeatable about the structure of a sentence. Every sentence is different, whereas the assumption here is that the structure is across time. There's statistics that sort of stay fixed across time, or at least they're slowly moving. So for such richer signals, we need different methods. Things like convolution don't really work very well. On the other hand, we also learned about dense networks, but we know that those don't scale very well. Those are quite generic, but it's expensive to have these large matrix multiplies. So in order to tackle this problem, this is like something people have looked at for many decades. If you go back, maybe about 10 years, the things that worked best were recurrent neural networks, or special varieties of those recurrent neural networks, such as long short-term memory networks or GRUs. And basically, in those networks, you have some sort of maybe dense network here that takes in the current feature vector x1 as well as some state and produces an output. And then for the next time step, you take that next input, and this RNN also updates the state. And so this is basically what's happening is this is being fed back to the input over and over again over time. And this is sort of just a visualization for how things change across time. But these were what people were using for text processing, and they work okay, but they don't work super well. And so so people were improving them. But eventually, this notion of attention and self-attention was proposed, and that created kind of a revolution in architectures and much stronger models. So any questions on anything here? The local, yeah.
So what kind of data are we strictly speaking about here?
You know, it turns out that the things we'll be talking about in this unit are very general. So what I mean is that, let's say if you want to work with text data, that would be one example. But if you want to work with images, even though convolution does work well with images, nowadays there's really powerful transformers that seem even more powerful than convolution. Although it kind of goes back and forth, because when someone claims transformers are great, then someone will say, actually, the reason your model is so great is because you're using the latest training tricks, and if I apply those to convolution, I'll show you that convolution works just as well. So it's kind of been going back and forth over the last few years, but basically, if you do look at what is in the very latest models, like the GPT-4o just came out with an image generation function this spring, and they are using transformers for images.
The main idea of these transformers and attention mechanisms arose because of the language processing, like context, is it?
Yeah, I would say language processing is like the key application, but I just want to say that the things we're talking about are not restricted to language processing. They could work for sequences, they can work for images, they can work for everything. They're just more general. Okay, any other questions? Okay, so let's kind of gradually build the idea behind self-attention. We're going to start really simple. But basically, self-attention is a way that we can characterize the strength of relationships among the different elements in an input sequence. And so we're always going to be talking about an input sequence of vectors x, xi, where I goes from 1 to t. And these are going to be d-dimensional vectors, just like all our features so far have been d-dimensional. And this length t is called the context length. And as we'll see, you know, the methods become more expensive as the context length increases, but all the same, they can be much more powerful. So when we will eventually look at how these modern transformers have evolved, we'll see that context length keeps growing and growing. And that's part of what makes the models more powerful. But basically, the context length is just telling us how many different items in the sequence we can process all together. Okay, so the x's would be the inputs, and then the y's are the outputs of this attention mechanism or self-attention. And from this equation, you can see that the ith output is just a linear combination of all t inputs. Now, we've seen things that look like this before. In fact, like this is the equation for a dense layer or a linear predictor, you know, missing the bias terms. But the key there is that these weights were learned. Here, these weights are actually not learned. What they are is they're computed from a softmax of what are called raw weights, the W primes, and the W primes are just inner products between the different xi vectors. Okay, so this Wij prime, like I said, inner product between xi and xj, and as we know, inner products give us just one way to compare the alignment of two vectors. You know, are they pointing in the same direction, opposite direction, are they orthogonal to each other, and so on. And as we know, that gives us some real numbers, positive or negative. And so what this softmax operation does is it takes, for any fixed I, it takes the sequence of these across J and basically converts it to a PMF. And so when you look at, for a fixed I, when you look at this vector of weights from J going from 1 to T, this you can interpret as a PMF because they will all be non-negative and they will sum to 1. That's what the softmax does for us. Okay, so basically what I'm saying is that these weights are not learned. They actually have to do with the similarity between the ith and jth word in the sequence, but then it's sort of non-linearly mapped to probabilities. So does this look familiar to you guys? Have we seen anything similar in structure to this elsewhere in the course? What? I see you nodding. Which one? No, I'm looking at the combination of the exponential and the inner product. Yeah, the radial basis function kernel, right? That's another place where we saw inner products that were stuck into an exponential. So there's connections there as well. In that case, we had a negative and we had a gamma, the kernel strength, but like, you know, that's basically using the same ideas to get a relationship between, in that case, it was different samples in the data set. Now it's different items in the sequence that we're processing. Okay. So this is, in its simplest form, self-attention. We're going to have to add some things to make it the real self-attention, but this just gives us the first inkling of the idea. All right, any questions so far? Okay, so one thing again I want to emphasize: there's no learned parameters so far. Although it turns out that these xi's could involve some processing stages before you get to this point that are learned. But the other thing I want to emphasize is that this model does not really care about the sequence order. Meaning if you shuffle the input order, all that happens is the output order gets shuffled. So this is called permutation equivariance. And in order to really teach the model that the beginning of a sentence and the end of the sentence and the middle of the sentence are all actually different locations in the sentence, we're going to have to add some additional things. Right now, we don't have that yet. We'll talk about that in a little bit. Okay, so this is just in its very simplest form. Any questions? Okay, so when you look at this equation, you actually notice that these xi's, that the inputs, are used in three different ways. So they are used as the things that are linearly combined to give you y. They are also used here in the first part of the raw weight, and then they're used again in the second part of the raw weight in that inner product. And the distinction here as to how the first and second parts differ is that when you look at the ith output, then, and you look at these weights wij, the first part in those weights is always xi when you're looking at the ith output. Whereas the second part of the weight here, that varies as you go across the xj's that are being summed for the output. Okay, so there's basically a difference in the first and second position in this inner product, the way this is set up. Okay, so again, these xi terms or x terms are being used three different ways. They're being used as the things that get averaged, and they're used in two different ways in the inner product. And so the next idea is that the fact that these are all very different roles for that same xi term. So probably we should add some extra learnable parameters that help us differentiate or specialize those roles. And so what we do is we multiply them by learnable matrices. So, and we call the results the query, the key, and the value. Okay, so again, maybe I should color code it. So the role here is called the value. That's how it's being used in that sum. Then the first part of the inner product is the query, which I colored green. So let me do that. So that's the green part. And then the key is blue. Okay, so for each one of these, we use a different matrix, and we title the matrix, oops, sorry. Okay, so we got the query, the key, and the value. These terms come from databases. I'm not a computer scientist. I may have taken a course that taught me that a long time ago. I don't remember. But if maybe you guys are familiar with that terminology from more recent computer, is that something you learn in computer science courses? Query? Does everybody know that? I'm just curious. Okay. Some people know it, some people don't. But basically, that's a terminology. It's sort of like if you have a lookup table. The lookup table is built in a certain way. You supply a new value where you compare to the different things in the lookup table, and then the closest one tells you which thing to return. So I think the thing you return is like the value. The thing you give it to do the lookup is the query, and then the things inside the table are the keys. So this is where the terminology comes from, but it's not important. You can just think of it as there's 3 different ways the XIs are used. And so what you do is you multiply each XI in that role by its own matrix. And then you see we have slightly different equations where now the values are explicitly here averaged to get our YI. And when we form the raw weights, we have the queries on the left and the keys on the right. Okay. Otherwise, the softmax is the same. Okay, any questions? Yeah.
So when we are referring for the item, so what do we mean by the item? Because
The ith output here. So yeah, so like I is just a dummy variable, right?
Yeah.
So here, like when you look at the ith output, let's just focus on I, meaning the output. Then you can see that it's taking inputs from all the different V's, right? From J going from 1 to T.
So that is the input is processed in sequence, right?
It's processed all together as one thing.
Not just the sequences from 1 to T, 1 to T, 1 to T, and that ranges as the I index.
So it's like the sequence that contains everything. This entire sequence produces an entire sequence of Y's.
That's all.
It doesn't happen like term by term.
Okay.
It's like the entire sequence goes in, and all these weights are computed.
So that entire sequence is the whole input.
Yeah, this entire sequence is the whole input, and this entire sequence is the whole output, and everything happens like kind of in parallel.
Okay.
Yeah, we'll talk about autoregressive later. I think that's what you're thinking about. We'll talk about that later.
No, I was just confused about how the input is and how it is processed. Is it just sequence, or the whole sequence is the entire input?
So this could be like a sentence,
Yeah.
and these could be the words in a sentence.
Yeah.
And so it's like you process the whole sentence at once,
Okay.
because you need to look at the end of the sentence to understand the beginning of the sentence, and so on.
So and also while doing this equation calculations, we are getting the XJs from the sequence, but and what is this XI then? So the XJs we are getting from the sequence.
Yeah. So we have a sequence, x1 through xt,
Yeah.
and I can use any dummy variable as the index.
Mm-hmm.
So here I'm using I and j as 2 dummy variables. So this means the ith element in the sequence. This means the jth element in the same sequence, right? And so if you think about this matrix of raw weights, this is a T by T matrix,
Okay. Yeah.
right? And then the softmax is applied across the rows of that matrix, not the columns, but the rows. Because this normalization is key to understanding the softmax. That's across the rows. So every row of the matrix gets a softmax, gets converted to a PMF. So if you sum each row, it would sum to 1. But if you sum the columns, they don't sum to 1. Okay.
So it's like in the matrix that you told, the Xij, the Wij, it will be a dot product between each input in that sequence.
Yes. Every combination of input and output will be 1 raw
Yeah.
W prime in that matrix. And then the rows get softmax to normalize them. Okay, any other questions? Yeah.
For the next slide, why do we have query and keep learner matrices both together? Because if you put them inside, just learning one of them is enough.
Can you say learning one of?
Query and keep both of the learner matrices because they just go into one equation and they can mix together inside.
So the difference is,
This kind of is unnecessary to have both of these matrices because finally they will mix together.
no, they play different roles. So the reason they play different roles is if you look at yi, the ith output, then all of these weights have the same I, right? And that means that they all have the same query. So when I compute yi, I have a single query, qi, that's used for all this, but the keys vary for every input. So that's why these have different roles. And that's why we have to think of them and treat them as different from each other. Okay, good. And there's one other thing we added here, which is a scaling term. And the reason for the scaling, if you remember, the softmax is sort of like a generalization of the sigmoid in the binary case to multiple. And so when you think about the sigmoid, maybe I'll draw it like this. If you go too far from the origin in the sigmoid, the output is very close to 0 or 1, right? And so if the inputs here are too large, then these weights here are essentially, they're almost 0 or 1. And that doesn't really work very well because you really want to have like, more of a mixing between these terms, not just have one of the terms come through and all the others are suppressed. So by making the inputs to the softmax a bit smaller, it gives that behavior. And this is the most popular approach that seems to be used by everyone now. There's other ones that have been proposed, but this is called scaled dot product attention. And the D dimension, this dk is the dimension of the key. So right now, in the way that we're describing it, everything is d-dimensional. So remember we said that the x's are d-dimensional, and then basically these are square matrices. But later, in just a moment, we will make these matrices rectangular, and that is why this could have a different dimension than this. And that's why we have to say which dimension are we normalizing by. Okay, so basically this is the famous scaled dot product attention that is kind of the heart of, is the known as self-attention. The reason why it's called self-attention is because it's the same x's that are used to form the query's keys and values. There's also such thing as cross-attention, where you actually mix two sources of information, and some of them you use for the two of these, and then the other one you use somewhere else. So I'm not going to get into any of that, but that's the distinction between cross-attention and self-attention. So far, or we're just going to focus on self-attention in this unit. Yeah.
I'm sorry, can you please repeat this concept once again, that the matrix is
This one, or?
the W, K, W, B, W, Q concept.
Are you referring to like why we need Q, why they play different roles?
Yeah.
Okay, so when you look at the ith output, all the weights have the same first index I, but J varies when you're constructing yi. So since the I term and the weight is fixed for, for all those terms, that means that they all use the same query. So for yi, qi is used for all of these, the same vector qi. But because yi sums over different j, where j is the second index, that means that all the keys are used to compute yi. Single query, but all the keys. And that's why they have different roles in this whole mechanism. Okay, great. Any questions? Okay, good. So, so now it turns out that what we described is still a bit too limited. If you take a look at the raw weights again and substitute in the equations from the previous page, this would be our query, this is our key. And now when you look at it and you step back and you just look as a function, how is this quantity going to change as I look at different ij combinations? And you notice that for every I and j combination, there's always the identical matrix being used here to form this quadratic form. And so in some sense, the method is not very flexible. Like it's kind of just limited because all these weights are, they all boil down to these matrices. So one approach to make this more of an expressive model is to, combine like a whole bunch of these. This would be maybe one, you could imagine stacking several of these in parallel, and then you could train a whole bunch of different triples of those matrices, right? That would be one thing you could do if you wanted to get a more expressive model. But the issue with that is that if we do that with the same full-size matrices, let's say I make 4 such self-attention units, now I'm going to have 4 times the complexity. And maybe we can get what we want without having the extra complexity. And the idea there is just to basically split each of these matrices horizontally. So if this is the key matrix, WK, this is WK, what we're doing is and this starts out as a square matrix, which is shown like this. We're just saying, let's extract the first quarter of the rows here. So there's going to be H submatrices in the picture here, H equals 4. And we're saying, let's think of this as, let's see, do I have the notation here? I guess the notation would be, this would be like the key for the ith vector, and then you use this superscript, just the superscript 1. And then this would be the key for the ith vector superscript 2, 3, and 4. And so because we have the same number of weights in the total matrix, it's the identical computation. But now what we're going to do is we're going to do separate self-attention, meaning separate softmaxes with the first elements. Okay, so this, maybe I didn't explain well. This is like the key matrix split into 4. This is the query matrix, and this is the values matrix. So we're basically splitting each 4 ways to get these submatrices that are wide submatrices. And then using these, we do self-attention. Now the dimensionality is no longer D, but it's D over H. So that's the new matrix has this dimension. And we go through the process, and that's going to give us 4 different outputs, each of them only 1/4 of the dimension. And then we can stack them back together to get a full dimensional Y again. And then we do one extra thing is add one more matrix at the output that we can learn. And this now is called multi-headed self-attention. So let me show you the picture. Maybe this will make things make sense visually. So here on the left, we have our sequence of xi's. And this would be for, this is like x1, x2, all the way to x5. This would be, sorry, this is like xi. This would be the dimension d, the number of features in each xi. And now the first thing we're going to do is we're going to multiply each of these by these matrices and then split them. So this is going to be for the first element in our sequence. This is that shorter key vector for the first head, the shorter query vector, the shorter values vector, and so on. And we do this for each of the different times in our sequence. And then these are the ones for the second part over here, this one, this one, this one, and so on down to the fourth part. So now that we have these shorter queries, keys, values, we do self-attention, and for each one of these, we get our output sequence. And now we're stacking the output sequence back together, and then finally doing one last matrix multiply of dimension d by d to get the final outputs yi. So this is the multi-headed self-attention that is basically used in all the transformers. And so you get the benefit of the only additional complexity really is the addition of this. But otherwise, all the matrix multiplies are identical in complexity to what we had before. I guess you have to do 4 different softmaxes, but that's not a big deal. Okay, so this is the so-called multi-head self-attention layer. That's really the basis for all the transformers these days. Okay, is this making sense? Any questions? Okay, great. Okay, so often when you see other sources, you'll see things represented as matrices. So let's look at how that turns out. So we have these xi vectors. So we're going to stack them as rows of a matrix X. So we're going to have like x1 transpose down to xt transpose. We're going to do that actually for all of our matrices. So we're going to stack the x that way, stack the y that way. We're even going to stack the queries, keys, and values. So these are all, they all have t rows. And the way we set things up, that transposition causes the weight matrices to move to the right and themselves get transposed. And then when you look at the softmax, this is that t by t raw weight. This is t by t. This is the raw weight matrix here. And then it gets, well, I guess it's the raw weight matrix before the scaling. Then that goes through the softmax. And then finally, this t by t multiplies by this t by d matrix to finally give you the output y stacked similarly. Okay, so this is just putting everything in matrix form. You get this, and this is what everyone calls the attention layer. And they usually talk about it in terms of the inputs being QKV. You could also think about it in terms of the input just being X, but this is how it's usually written. Okay, so you got the raw inner product here, then you got the softmax, and then you got the linear combination to form the output Y. Okay. All right, so any questions on this, or is that making sense? Okay. And then if you want to write multi-headed attention, essentially what people do is they look at any of these matrices. I'm just calling them W star here to mean any of those. And you multiply them by what I call a selection matrix. So the first selection matrix would have an identity here, and then zeros, this would be a wide matrix. And multiplying by that selection matrix would just extract the first bunch of rows from this and put them in this. So that's what the different P matrices do. They just extract the different sets of rows. And so now multi-headed attention can be used or can be written in terms of this attention here by just extracting the appropriate rows of the query key value, putting that through the attention, and doing that for each of these different H heads. And then here we're stacking things as columns of a matrix, and finally multiplying on the right by this combining matrix WO. Okay, so this is multi-headed attention as it's often notated. Okay, any questions? Okay, great. So, all right, so now we learned about attention, basically the fundamental ideas. And so how attention is used is in these transformer blocks. So here's an example of a transformer block. Now there's different variations, but surprisingly, from what I've seen, they don't actually vary too much. So the main ideas that we have here is we have our self-attention, and it's usually the multi-headed self-attention we just described. So that's this block. And then we have layer norm. Layer norm is just like batch norm, but instead of averaging across batch elements, it averages across features. And it plays the same sort of role as batch norm. It's there to help normalize everything, make the training more robust. And then over here, we have a bank of MLPs. And these are just 2-layer ReLU networks, exactly what we saw in Unit 8. And from what I've seen, they usually choose the number of hidden nodes to be 4 times the input dimension. So they just go up by a factor of 4, come back down. And these are often called the feed-forward networks. And each MLP is applied separately to each sequence output of, so basically, yeah, so here, you coming out of the self-attention, in this case, we have t equals 4 in this picture. So coming out of self-attention, you would also have a sequence of 4. The layer norm just basically normalizes each of these separately, for each time I, and then the MLP also applies to each output separately. And the final ingredient we have is skip connections around the self-attention and the MLPs, just like we saw in the ResNets. So that's it. This is how it was done in the earliest papers. In later papers, they figured out that it's better to put the layer norm in front instead of behind. And so this is called post-layer norm architecture, and it's better to put this in front because the training is much more stable. But otherwise, from what I've seen, they still use this architecture like this. There's some modern ones that use like a smooth instead of a ReLU. They use like some GeLU or something, but otherwise, it's basically just this. Okay, so this is a network that takes in a sequence of these vectors xi and gives you and outputs a sequence of the same dimension and of the same length. Okay, any questions on the transform blocks? Okay. So how do we then use this for classification, for example? So what we do is we actually stack a bunch of these transformer blocks together. In this picture 3, more typically it might be like 12 or something. Not an incredible amount. And so let's say that the input sequence, so in this classification task, as an example that one of the early transformers trained on, you have movie reviews. These are, like text sentences. and you're trying to predict whether the review is positive or negative. Is this, and so the transformer is going to have to learn to pick up on keywords, but also to, put them together, like figure out that double negatives are negating each other and, actually a positive and so on. So anyway, we take our input sequence. We'll talk about how we make this into numbers, but that's another thing we have to do. These are called word embeddings. Those are our XIs. We put that through these transformer blocks, and we get our output sequence. And now, because we're doing classification, we don't really want any time axis anymore. So we just average these across time. We average them across time, and we're going to get something of dimension d, if d was the input. So this is going to be a d-dimensional vector, but we want to classify in dimension k, meaning we have k classes. So there's a dimension mismatch there. And so all we do is we put it through one learnable linear layer at the end, which takes our d-dimensional time average output and just basically learns how to convert that to k-dimensional with some weight and bias. And now that gives us something that has dimension k. In this example, because k is 2, it made a vector of length 2. As we know for binary classification, it's enough to just have a single one. You don't need a vector of one hot coded 2, but you could do it. So here, like the target is one hot coded. But if you had 3 or more classes, then you would need this to be 3 or more, and so on. And everything, of course, is trained according to the usual cross entropy loss. We're learning jointly these weights and biases. We're learning all the transformer matrices, and that's it. Does that make sense? That's one way we could use it for classification. Now, there's something important that's missing. Remember how I said that the transformers were permutation equivariant, which means that if you shuffle these words in the sentence, that means the output of every transformer will just be shuffled, right? And so that means the output here will be shuffled. But then when you do the time average, the shuffling vanishes. And so that means, for example, if you had the sentence man eats dog, that would give you exactly the same y as the sentence dog eats man, right? But that's clearly a problem because they mean very different things. So that's why we need to add one more thing, which is position embedding. That will actually tell the transformer that this is the first word in the sentence, this is the second word in the sentence, and so on. And then it learns to interpret word order in addition to the words themselves. Okay, so that's this notion of position embedding. And the way that it's done is surprisingly simple. We're just going to come up with some vectors, and we're going to add them to these word embeddings, the XIs. We're not going to concatenate them as you might think. That would increase the dimensionality, which would cause the transformer blocks to have to do a lot more computation. So instead of increasing the dimensionality by concatenating, it literally adds them. So this is how it goes. We add a vector ti to each xi, and the ti tells us where in the sentence we are. And there's basically 2 different ways to do this. There's so-called position embeddings, where what you do is you treat those ti's as learnable parameters, and you learn them jointly with everything else. And then the other option is you don't learn them, you just set them as some fixed sequence of vectors. And the most famous one is called sinusoidal embedding, which is based on a sine and a cosine. It's very much in the spirit of a Fourier transform. Here, I is it's basically the sequence index. And then this is sort of like a frequency, and you can see the frequency changes as you go through the dimension k in this vector. So as you go, and there's basically d elements in this vector. As you go down there, the exponent here changes, and n is some large constant that you choose. So the picture kind of looks like this. Here we have position, I. Let me write. I is in 1 through t on this axis. And then we have vector index, I think I called it k, which is in 1 through d on this axis. And you can see that these are, so basically the even ones get a sign and the odd elements get a cosine. And so when you look at the even ones here, these would be signs of decreasing frequency. And then the odd ones would be cosines of decreasing frequency. Okay, so that's position encoding. Position embeddings also work, but one of the issues is that you kind of need to know the length of, your training set has to have sequences of all different lengths, otherwise you might not learn some of those TIs. You might not have enough examples to learn them. Okay, so I think nowadays this position encoding is more popular than the embedding. Okay, all right, so that's what we're doing here. Okay, so any questions? Is this making sense? Everybody good? Okay, great. So let's come back to the these XIs. How do we actually create the XIs? Because we've been talking about using text, but the XIs are actually vectors of real numbers. So we have to talk about how we go from text to these real numbers. And so, and we can do the same thing with images. We can describe that too. So with text data, there's actually 2 steps. The first step is called tokenization, which converts text to integers. And then the second step takes those integers and converts them into real numbers. Okay, so let's talk about the tokenization. So there's different ways to do this. The earliest transformers, simpler, smaller ones, basically they didn't go word by word, they went character by character. And so they wanted to handle characters from many different languages around the world, not just English characters. And so they used this UTF-8, which is like an international text standard that tells how many different characters are coded, and it's in sequences of bytes. I think the most common characters just you use 1 byte, and the infrequent ones you use several bytes. But basically, this so-called byte pair encoding scheme goes character by character, not word by word, and it converts those characters into these numbers, these integers, as the tokenization. So later methods started looking more at the word level, or not quite at word level, a little bit sub-word level. So for example, like the word walking could be broken into walk, and then the extension ing, and you would code walk, as one integer, and you'd code the ing suffix as another integer, and that way you would learn to, you could kind of learn that all the different walk words have something in common, like walking, walked, walk, walks, and so on, and then all the different suffixes have something in common. So that would be word piece. And then there was another version that said, well, wait a bit, not all languages in the world actually use spaces to separate the words, so this sentence piece was sort of a generalization of word piece that was more transferable to other languages. Okay, and there's custom versions of this stuff that's used in some methods, but these are sort of the things you find. So we're starting with text data, and we're converting them to integers. And we'll see some numbers later, but maybe you have like 50,000 possible integers for each token nowadays. Okay, now that you have these integer tokens, you basically learn a code book as a way of representing xi. So if I have 50,000 tokens, I need to make a matrix that has 50,000 columns. And if I have token equal 10, that means I will take the 10th column from this matrix and assign that to xi. Okay, so these are columns of real numbers that we learn. So that's how you go from tokens to embeddings or features. Is that part clear? Okay, now what about coming back? If I have a vector of dimension xi, let's call it yi, and I want to say what is the token that corresponds to, it might not be any entry in the code book, right? It could be, because you can kind of visualize the code book as a bunch of points. And then the entry that we actually have would be somewhere in between those points. So it doesn't correspond to any particular entry in the code book perfectly. And so really, when you think about unembedding, instead of getting a single code book entry, you could look for the closest one. You might actually want to know like a PMF over all the closest ones, or maybe even all of them. So if the closest ones would give you the highest probabilities, and the farthest ones the lowest probabilities, and so on. And the way to do that is you take that output, and then you learn a matrix and a bias that convert that to a vector of real numbers, which you put through a softmax. And this is a dimensional n, where n is the number of elements in the codebook. And now you have a PDF over those n possible words. Okay, so given an output from your transformer, you can look up and basically say like, okay, with 90% probability, it's this word, but with 5% probability, it could be this, and 2% it could be this, and so on and so on. So that's what it gives you on the other side, the unembedding. Okay, all right, so that's what we do with text. Any questions? All right, so what do we do with images? So the very first approach for images and transformers was called the vision transformer. And what it did is it broke up a larger image into 16 by 16 patches. And a patch is just like, little rectangular, or actually square pieces. It just broke the image into those little patches, like that. 16 by 16. And then it flattened them. So now we have a 256 dimensional vector. And then it did linear coding, meaning it learned a C matrix and a B vector that gave an X vector of whatever dimension you want. So if you want to save on complexity, you make this a wide matrix, and that means the dimensionality here would be less than 256. Maybe it's quite small dimensional. But if you can afford a more complicated model, you could even use a tall matrix here, in which case these outputs would be greater than dimension 256. Okay. But basically, that's all you do, is you take image patches and you code them. And in terms of the order, I believe that first paper just went through like, row-wise. It just took the first row of patches, then the second row of patches. So basically rasterized it into one sequence, went from 2D to 1D. And then it just basically treated them as words in a sentence, more or less. Simple as that, and it worked. Now, there's more sophisticated approaches. So like the one that's used in the most recent image generation models in ChatGPT or GPT-4o is this vector quantization variational autoencoder. And basically, what it does, we talked about VAEs back when we were talking about neural networks. But the VAE it has an encoding function and a decoding function. The encoding function takes an image. This is of size height times width times 3 because we have 3 color channels. And it converts it to another 3-way tensor, but it downsamples the height and width by a factor d. Typically, d is like 16 or so. So now you're going to have 1/16 the pixels, both horizontal and vertical. But then it grows the number of channels from 3 to something bigger, like maybe this grows to 16 or 64 or something. But overall, the number of entries in this tensor is less than the original one here, so it does some kind of compression. So these are still going to be real numbers. So the next stage is to quantize them. And so we then quantize these real numbers, again using a codebook, where we choose, here, n vectors in our codebook. And basically, this is exactly the problem we talked about at the end of the last unit, when we had all those different colors, and we wanted to figure out, like, what are the 16 best colors to represent 17 million colors. That's what we're doing here. We're saying, what are the n best colors to basically represent all the, okay, if this is a three-way tensor, where this is height, width, and channels, we're looking at each one of these vectors alone. This is like the ith pixel, which I'm calling this, which is a c-dimensional vector. So for each pixel, we're basically saying, and this is more than 3 colors, maybe like 64 colors. We're saying, what is the vector? If I can choose n different vectors to code these, what should they be? So this is a clustering problem that we saw how we can solve that. And then finally, we train a decoder so that we can take that quantized latent representation and come back to the image space. And if we design the encoder and the quantizer and the D well and jointly, we don't have much of a loss in this operation. So basically, this is a more sophisticated way than just doing this up here. And there's also methods that if you want to jointly embed text and images, which is useful, like if you want to generate images from captions and captions from images and so on, then you can come up with an embedding space that merges text and images, and the most famous approach to that is called CLIP. And this is an example of multimodal learning, where you're not just doing learning with images or learning with text, you're learning jointly with images and text. And that's also something that is in the latest GPT models. Okay, so sorry I went on a little bit. This is a good time to stop. Let me know if you have any questions. Otherwise, see you guys on Wednesday.